Oliver, and our sponsor, Tim Potter, and our facilitator, Dr. Chuck Potter. We're going to start off with our demo video.
Small crowd. Yeah.
Do we need that sound?
Should be.
Maybe connect to it.
Need one Ethernet. Did you play song in Mexico? Play something.
That's not good.
Into one of these stories.
A bright future.
That's okay.
That's fine.
Imagine a future. A bright future. A future of zero accidents. A future of exploration. A future of education. A future of health. Imagine no more. Introducing the MSU Green Box, a data collection device that can track sudden or hard braking from the rider, collision detection, all of your rider data right at your fingertips. Featuring cutting-edge and sophisticated hardware architecture, such as 9-axis accelerometer and gyroscope, integrated Bluetooth module, GPS functionality, battery powered, with charging capability, a much more compact and sleek design profile. The box features a robust and sturdy C-clamp design, ensuring a quick and frustration-free installation onto any bicycle. Discreet and convenient for any cyclist. Unobtrusive, while also easily accessible. Simply download the dedicated mobile app connected to your mobile device via Bluetooth. Press the record button on the app to begin a ride. All the important rider data will then be displayed on the app. This includes accelerometer and gyroscope coordinates, GPS latitude and longitude, and rider speed. You don't need to wait for the future, because the future is already here. Are you ready to take a ride into the future with the all-new MSU Green Box?
Nice. Great.
Alright,
you can see from the video, we were basically taking the MSU Bikes data collection device for bicycles and completely redesigning it for this year. And to do that, one of our main objectives to be adding a Bluetooth connection system this year in order to make the data collection form more seamless and much more reliable for the user. They can then use that Bluetooth connection to pair it to a mobile smartphone application to allow them to view the data and telemetry of their rides in a much more convenient manner. And we also want to make sure that we did extensive field testing, putting in many rigorous situations in order to understand the nature of different bicycle incidents and crashes. The additional objective that we wanted to make sure that we did was make sure to create a new hardware design completely from the ground up, not just from the previous design. And so we wanted to do that by making a PCB design that we could put together in a much more compact and neatly designed package.
As for our adopted design approach diagram, here's our hardware. Our microcontroller collects all this data from the various modules that would be further emphasized in future slides, and goes through the Bluetooth, and the Bluetooth sends over the data to their smartphone application, which is then usually shared by the user.
And so like I touched about in terms of our long-term goals of this project, we really just try to collect extensive data as well as develop the application. So to do that, we added a Bluetooth module to the prior hardware using S-track communication. And as you can see in the second image here, we did create new housing and we did rewire the complete system to make it fit in that housing, as well as we did convert the two-bus system into a one. And the reasoning behind that is that on the application we can actually start a ride, so there's no need to start the ride in the box as well. And with that, we also did remove the SD card because the phone could save the data. And so in terms of our new hardware, actually some of the guys are going to hand out copies of the PCB that we did develop. Everything is labeled on it, all the modules. So what it contains is an STM32 microcontroller, a Neo 6N GPS module. It does contain a 9-axis inertial measurement unit with the gyroscope and accelerometer on it. And then it does contain a power charging module, which will actually power our battery, which will charge our battery via micro USB. And then from there, it goes into our voltage regulator at 3.3 volts to regulate the system. And then it also does have a 10-pin programming connector for the microcontroller, so we can download code onto it and program it. And to verify that all of this was going to work, we did build a prototype at the bottom right here. So you can see that to make sure that our functionality was going to be verified and that it was going to work.
Through the PCB development, we were able to accomplish a 51 decrease in the overall size of our new design based on the previous design. And over here, I'm going to pass you guys two size comparisons from the previous team as well as our new design iteration. We did three major design iterations. One was, of course, the incorporation of and removal of the lids. As you can see, the lid on the 5 no longer has a slit, just because that slit was used to store the antenna. This was removed because it served as potential damage to the antenna, just because it hanged off one wire. So when you remove that lid, damage can be yanked off by the antenna. We also incorporated various. Second design iteration was the battery pocket, as you can see in figure 6. We wanted a tighter tolerance for that pocket rather than a battery be moving around when the light is in riding mode. And then the last design change that we did, we incorporated various design features on the outer portion of the box, like the MSU Service Center logo, as well as the MSU helmet logo on top of it. We did keep the same hardware for the micro USB port for charging, as well as the outer steel button outside of the portion of the box, just because these did serve as weather resistant, and that's our just because we were considering environmental factors as well.
So for the Arduino software, we redesigned and optimized the code in order to accommodate our new SPI Bluetooth module, as well as we changed the way that the data is being stored. So it's since we removed the SD card, it's no longer being stored to the SD card, and instead being sent via Bluetooth to the device, or to be stored on the smartphone app.
In terms of smartphone application, we created designs of different views along with the navigation for each different views. We also created a backend where we store each ride. I'm going to show you a live demonstration of the application with collision detection. I'll show it myself. So from the application, from this the home display, we can start data collection and connect it to peripheral. And for here, we can start the data collection. Top here we can see accelerometer data, and the bottom second one is the JavaScript data. Those are X, Y, Z, all three axes. We got to see speed and GPS on the lab, but currently since we're indoors, it's all not catching a signal.
I have a quick question. So this one you're connecting, right? Is this your new version or the old version hardware?
This is the updated, the first new version. So we added the Bluetooth module to the old hardware and then changed the code so that it would be compatible with the
So
app.
this is the old hardware, but with
Yes.
a Bluetooth module?
Yes.
So I have to demonstrate a collision where you can go forward and to the side. So as you can see, this is a short section of data before and after the collision. So for the route. After we end the data collection, normally up here there would be a green path for the route, but since there's no signal, you can't see the route. You can see the overall data from the accelerometer, gyroscope, and along to GPS, different metrics. Here we save it, and from the history tab, we can view our history. Again, same thing, this is from the route, but due to no signal, we can't see it. We got to see different metrics for the overall ride. We got to see different reports that occurred. So as when Josh did a collision, see there's one report, and we got to see the types of collision, and we got to see the specific spike of the gyroscope, which is the difference between the hard braking and the collision, main difference. And the collected data is just raw data that we can parse later. On reports, this is all reports that occurred for any ride. And as you see the hard braking, we have the orange banner, and this is the route of the map. Normally, just would be working.
So we also created a machine learning model in order to help us detect braking and crashes. This is an LSTM model, which stands for long short-term model, and it essentially looks back in time at previous timestamps of data in order to predict the next outcome. So it takes a CSV file as an input, and it would look at previous timestamps to predict whether the bike is currently braking or riding normal or crashing. As you can see in the figure on the right there, it is currently trained at about 70% accuracy.
So what you just showed that a collision detected, was that using this threshold test?
Just special case.
Okay. So this is the Gantt chart that we had created at the beginning of this project to make sure that we can schedule and organize the deliverables during the timeline. Overall, we did schedule very well. We did adapt accordingly, and we managed to have some constraints within our timeline. So of course, the Gantt chart is a living document. So at any time during the project, there are going to be changes that need to happen to come with any engineering project. So those constraints involve things like the delivery time it took when ordering our PCBs to get those fabricated, along with the time constraints that came with programming the microcontroller, and then the creating machine learning model. We had instances where Josh was using one machine learning model that was simply not working, so he had to cut his losses and switch to the PyTorch model. And so those were just some of the constraints that we had to deal with.
So in terms of our budget, on the left is going to be the new design with the PCB hardware, which comes around just under $100, and the prior design with the Arduino came around just under $150. So there is around a $50 savings with using the PCB. So I think budget-wise, we're very cost efficient this semester.
As for future steps, we want to continue to PCB program and design, so we want to consider alternative IDEs such as Keel. This would be to access for easier compatibility with the microcontroller, as well as the ease of use, just because we ran into a huge programming issue, as well as conduct a thorough review of the PCB design, just because through our prototyping, we were able to say that it did work, but we want to continue to assess that just because we can get too fully integrated into our new design. For housing, we also want to weather test the whole box by itself, not just the components that are weatherproof, just because we think that water damage is bound to happen on the bike application. As well as source any new ports or buttons that could further take down the size of the box itself, just because of the ports that we currently did have in there took a lot of space within the box.
As for the software, we think it'd be beneficial to start collecting a large amount of what we call real ride data, so like rides through campus during busier times of day, and longer rides that are like 5, 10 plus minutes long. And then use that data to better train the machine learning model, as well as integrate the machine learning model into the software application.
To go on what Josh said, with more rides and more incidents would occur, I guess we can create a hotspot map of different incident locations along campus.
Okay, so let's give it a round of applause.
Is Alan correct that the data is pretty much anonymous? I mean, you see an accident has occurred, but you don't know which bike was involved, or it seems like associating the detector with an individual bike would be kind of important to get an identification.
That wasn't in our scope. We thought about making different user profiles for our application, but we decided that it would be more beneficial to focus on the main functions, like of the brake detection and everything, as opposed to making the multiple users at this point in time.
I think the model is, Steve, is that this is owned by the bike owner. So essentially what you do is that it's on your interest that you just put it on a bike, and then when the bike comes back, right, then you get all this data. So identity is kind of integrated with the model.
So the data would come from the actual bike rental or whatever you want to call it. Okay.
So one of the things that I think team is going to be able to do it, explain it better, but the idea is that when you're renting the bikes out, right, then you want to know that how the bike was handled, and based on that you streamline your repair schedules and things like that.
And it's also good for traffic engineers and designers of the transportation system, to see where are the problem areas, where can we improve things to avoid more potential crashes, because a potential or a near miss or a sudden deceleration without an actual crash, it could have been one second difference, and it might have been a serious crash or an injury. So
now, so I think nevertheless, what Steve was saying, that is going to be important when you. Oh, since the other guys joined. Yeah, so when the data is kind of uploaded to the cloud by the box directly, right? In that case, the identification of the, which bike it is, who was the ride, having a ride, and all this information becomes more important. That's true. So eventually, I think that needs to be handled. So overall, I thought that you guys did an excellent job. Yeah, I mean, I remember that you had some difficulties with the new hardware. There's some. But looks like that you have gotten over it, or that you're still kind of...
So we weren't able to completely program the microcontroller, but through our prototype, eventually we actually had a faulty link. So when I reached out to the microcontroller company, they actually had told me to double check some of the interior of the link, and so one of the pinouts was actually bad on it. So we wasted about 2 weeks on that. But we were able to program like very simple functions through a microcontroller on the prototype board to verify that it did work. So we were able to program the model.
Okay. All right. So for the sake of time, I think we should wrap it up now. But yeah, excellent. Thank you.
Great job, guys.